Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. We have successfully completed module 3 of the course, which was on process management and process scheduling on Linux based systems. This module is basically about inter-process communication. We will have quite a bit of sessions on this part of the subject, inshallah. Let us see what all is there on today's agenda. First of all, we will see different ways using which different UNIX processes share information. Then we will have a discussion on the taxonomy of inter-process communication and the persistence of different IPC objects. And in the second part of today's session, we will discuss the concepts of signals, and we will see how we can use these signals on the shell. Okay, we can design an application program using these three ways. And if we use option 3, that is spread our program logic among different processes using fork, the biggest question is how can these cooperating processes running in different address spaces can communicate with each other. That is how one process can pass some input data for processing to another process, and after computing the result, how the other process can return the result back to the first process. Well, this slide shows 3 different ways using which processes can share information with one another. The first way is really the old way, and it is actually very slow as well, in which 2 processes communicate with each other by reading and writing disk files. And there is a mod switch which is involved, as well as there is a electromechanical disk that is involved, which is very slow. The second way, which is the actual inter-process communication way, is that we create an inter-process communication object in the kernel space, and the cooperating processes running in the user space reads and writes data in this IPC object. And there is of course a mod switch from user space to kernel space is involved, but there is no slow disk involved as in this way. The third way, which is the fastest, is the shared memory, in which one process shares some memory region within its address space with the other cooperating process. And of course this is the fastest because there is no mod switch involved in it. Let us see these in detail. Well, dear students, the subject of inter-process communication can be divided into these 3 main categories: communication, synchronization, and signals. Let us discuss them one by one. Okay, the communication category can further be subdivided into 2 flavors: the data transfer and the shared memory. In data transfer, all the data transfer techniques have destructive read semantics, and the synchronization between the reader and writer processes is implicit, that is handled by the operating system kernel. On the contrary, in shared memory, this allows processes to exchange information by placing it in a region of memory that is shared among the cooperating processes, that is, no kernel is involved. Moreover, this shared memory has non-destructive read semantics, that is, data placed in the shared memory can be read by any number of processes any number of times. However, synchronization over here is not implicit. Rather, it is the baby of the programmer. Okay, well, this data transfer facility, this can further be subdivided into 2 subcategories: the byte stream and message passing. In byte stream, each read operation may read an arbitrary number of bytes from the IPC facility, regardless of the size of blocks written by the writer. An example IPC tools that use this technique are pipes, FIFOs, and stream sockets. In message passing, dear students, each read operation reads a whole message from the IPC facility as written by the writer process. And it is not possible to read part of a message, leaving the rest in the IPC object. Nor it is possible to read multiple messages in a single read operation. And example IPC tools that use this technique are message queues and datagram sockets. Well, there are two implementations of message queues available on Linux, one using the System 5 API and the other using the POSIX API. Well, as far as this shared memory is concerned, most of the modern Unix-based systems provide three flavors of shared memory. And these are System 5 shared memory, POSIX shared memory, and memory mappings. We will see all these in detail in our future session, inshallah. Okay, so after the communication category of IPC, let us move on to the second category, and that is synchronization. Well, synchronization facilities allow processes to coordinate their actions in order to avoid simultaneous updating of shared variables in the shared memory regions, thus causing an application program to produce incorrect results. Most of us have seen this in the operating system concept course. And the first subcategory that falls under synchronization are the semaphores. The two famous implementations for semaphores are using the System 5 API and the POSIX API. Well, if we want to synchronize among POSIX threads, we can use mutex and condition variables. And we have discussed in the operating system concept course that mutexes are used for locking, while the condition variables are used for waiting. Well, the third subcategory for synchronization is explicitly designed to coordinate the actions of multiple processes operating on same files or part of the same file. And I think we have seen its usage while achieving file locks and record locks using the F control system call. And of course we will see these semaphores and mutexes in our future sessions, inshallah. Okay, after the communication and the synchronization category of IPC, the third and the last category are signals. And we have standard as well as the real-time signals. And these signals, as we all know, are used by operating system kernel to notify processes that some event has occurred, without these processes needing to poll for that event. Okay, dear students, the term persistence refers to the lifetime of an object. And let's talk about the persistence of IPC objects. There are three types of persistence: process persistence, kernel persistence, and file system persistence. A process persistent IPC object lives as long as it is held open by at least one process. Pipes, FIFOs, sockets, mutex, condition variables, and read-write locks are all process persistent. A kernel persistence IPC object lives until either it is explicitly deleted or the system reboots. A message queues, semaphores, shared memory, these are at least kernel persistent. And the third level is the file system persistence. And a file system persistent IPC object lives until it is explicitly deleted or the file system crashes. And the examples are message queues, semaphores, and shared memory if implemented using the memory map files. Okay, so that is the overview of inter-process communication. Let's have a quick recap of signals. And we have talked about signals in the operating system course as well. let me have a quick review of all these. Okay, dear students, suppose a program is running in a while loop and the user presses the Control plus C key and that program which is running in the foreground dies. How does this happen? Actually, when the user presses Control plus C key, the TTY driver receives a character which matches the interrupt character. The TTY driver calls the signal system of the operating system, and the signal system sends sigint to the foreground running process. And when the process receives that signal, it dies. And we know we can always change this key combination for different signals using the stty command or the tcset attribute system call. Well, we can say that a signal is a software interrupt delivered to a process by operating system because the process did something. For example, a division by 0, in which case sig fp is delivered to that process. Segmentation violation, sig ill, which is sent to a process in case if it tries to execute an illegal instruction. The other reason of delivering a signal to a process by OS can be the user did something. That is, the user gave some key combinations and gave sig int, sig quit or sig tstp. The third reason can be one process wants to tell another process something. For example, the sig child signal is given to a parent process once its child terminates. So a signal can be defined as that they are used by operating system to notify processes that some event has occurred without these processes needing to poll for that particular event. And whenever a process receives a signal, its execution is interrupted from whatever it is doing and it is forced to execute another piece of code that is called a signal handler. And when the signal handler returns, the process continues its execution as if this interruption has never occurred. A signal handler is nothing more than a piece of code that gets called when a process receives a signal. And every signal has a specific handler associated with it, which can be called in the asynchronous mode or maybe the synchronous mode. Well, a synchronous signal actually pertains to a specific action in the program and is delivered during that action. Most of the errors that occurs in our programs are given synchronous signals. And a synchronous signal is also generated on the explicit request by a process to generate a signal for itself. The other category is asynchronous signals, which are generated by the events outside the control of the process that receives them. These signals arrive at unpredictable times during execution. And the examples can be some external event generated asynchronously and maybe on the explicit request by some other process to generate a signal for some related process. Okay, so this basically shows you an illustration that describes what happens when an executing process receives a signal. Suppose this is a piece of code which is running, and once this execution reaches instruction N, a signal arrives. When the signal arrives, the execution of this code is stopped and the control moves on to some other place. Actually, the kernel calls a signal handler function on behalf of that process. The code in that signal handler or the function is executed, and after it is executed, it returns to the same place from where it occurred, and the program resumes at the same place its execution, and the execution continues from the next instruction, that is n+1. So this is how a signal is delivered to a process, and this is how a process responds to a signal. And the function, the piece of code that is executed once a signal is received is called a signal handler. Okay, dear students, let us now move on to the Linux terminal and make our hands dirty to understand the working of signals, their dispositions, and the concept of masking of the signals. Okay, I've given a wrong password. That is very bad. Okay, this time it's correct. Let us first view all the signals that are supported on our system, and this can be done by kill-l command. About 32 standard and 32 real-time signals. Every signal has an associated number and string constant. For example, this sig int is the string constant and 2 is the signal number, and these constants are defined in a file that is usr include asm generic signal.h. Okay, so these are the signals you can see. These are the constants that are defined. Fine. Well, dear students, this sig int is the signal that can be sent via keyboard by pressing Ctrl plus C character. Sig quit is a signal that can be sent via keyboard by pressing Ctrl plus / character. And the third signal which can be sent via keyboard is this sig tstp, signal number 20. Suspend signal by pressing Ctrl plus Z. Okay, this sig hub, signal number 1, is sent to a process when the user who ran the process logs out. Okay, what else is important? Find this sig term, signal number 15. This is the default signal sent by the kill command, and is also the signal sent by the shutdown process to all running processes before sending the sig kill. This sig ill, signal number 4, this is a signal which is sent by the operating system to the process if it tries to execute an illegal instruction. This signal number 8 is sig fpe, which is sent to a process on division by 0. This signal number 11, sig seg v, this is sent to a process by OS if the process tries to access some unauthorized memory. Well, we can write the handlers of all these signals except 2, which are called the known catchable signals. And the known catchable signals are signal number 9, sig kill, which is also called the silver bullet, and this 19, sig stop. Do see the details of rest of the standard signals as well, and let us move on to the concept of signal disposition. And let me show you this from the man page of signal. Do read this man page, it's very informative. Well, by signal disposition, I mean what will happen when a process will receive a signal. The current disposition of a signal actually determines how the process behaves when it is delivered signal, and these are the behaviors. The behavior can be term, that is terminate the process, ignore, that means ignore that signal, core means terminate the process and generate a code dump file, and that code dump file can later be used for the process postmortem. This stop is the disposition that is used to stop the process, stop the execution of the process, and this continue is used, whose default action is to continue the process if it is currently stopped. Okay, and you see the details from this page. Let me move to the terminal, clear screen. Let us run a program and send it some signals. Let's suppose I run a program sleep 1000. This process is running in the foreground right now. Let me suspend it by pressing Ctrl plus Z. I have pressed Ctrl plus Z. By pressing Ctrl plus Z, I have sent actually the TSTP signal to this, and its execution has stopped. Let me check out using PS-L. You can see this is the sleep process, and its state is T, that is stopped by a job control signal. Let us send it a continue signal to start its execution in the background. And to send a signal to a process, we can use the command kill. Do read the man page of kill. And let me send SIGCONT sig continue to the process sleep having the ID 2925. Okay, fine. And let me check out now PS-L again. You can see the state is now S, and S means interruptible sleep, that is waiting for its turn, maybe in the ready queue. Let me bring it to the foreground now. It is running in the background. Let me bring it to the foreground. Let me use the jobs command. It says it's running in the background. Let me use the FG command with the job ID that is 1, and you see it is now running in the foreground. Let me terminate it by sending a signal that is SIGINT, and that can be of course done using the kill command as well as by pressing Ctrl plus C. Let me press Ctrl plus C. So it is terminated, and you can check out there is no sleep process running anymore. Remember the kill command, using the kill command you can either mention the PID of the process or maybe the name of the process. And if you mention the name and there are more than one process is running with that name, all of them will be killed. So better to use PIDs. So far so good. So now let us move ahead and see how can we make a process ignore a signal, or write our own signal handler of a particular signal on the shell. This can be done on the shell using the trap command. Let me get some help about the trap command. Oops. Okay. Well, trap is an internal command, I think. Well, yes, this is a built-in. And to get help about the built-in, we use help trap, and let me pipe it to less. So this is used to trap signals and other events. Do see the man page or this help page. Okay. So if I use trap -L, so this is similar to kill -L. It displays all the signal numbers and the names. And if I use trap -P, well, it displays all the signals that are trapped right now. And right now there is no signal that is trapped. Let us try to ignore a signal. For example, let us try to ignore SIGINT, that is signal number 2. That can be sent via keyboard by pressing Ctrl plus C. I say trap and I say 2. This 2 single quotes with nothing in between means I just want to ignore it. Now let me check out trap -P. You can see that I have trap for SIGINT, that is nothing, and this will of course make the shell as well as all its child processes ignore SIGINT. Let me again run sleep 1000 and let me press Ctrl plus C. You see, I press Ctrl plus C and it is just displayed or echoed on the screen. No SIGINT is given to this process. Let me press Ctrl/. Well, this sends the SIG quit successfully and the sleep process terminates. Okay, let me ignore all the signals that can be sent via keyboard, and I can do that using trap 2, that is sig end, 3, that is sig quit, 20, and that is TSTP, and let me ignore signal number 9 as well, the sig kill, the silver bullet. And you can see all these signals are apparently ignored. Let me run sleep again. Okay, let me come on to terminal over here, and let me check out ps-a. You see sleep is running with the ID of 2953. Let me copy this and let me send SIGINT or signal number 2 to the sleep process. Remember, the sleep process is running over here on this terminal, and once I press enter, this SIGINT is given to it and it has ignored it. Let me pass sig quit, and it has ignored it. Let me pass the silver bullet, that is signal number 9, sig kill, and you see it is killed. Although the sleep process tries to ignore this signal, but it cannot be ignored. Remember, I just said a while ago that there are two signals which are non-catchable. That is, you cannot ignore them, you cannot write their handles, and they are sig kill and sig stop. Okay, now let us try writing a signal handler for SIGINT. Okay. Okay, right now there is no signal that is ignored. Let me write down a signal handler. Let me say trap, and let me say go. Learning is fun with Arif 2. Okay, so now this signal has this signal handler. This is the command which will be executed whenever a SIGINT will be given to the current shell. Let me send a SIGINT to the shell process by pressing Control plus C. You see, I press Control plus C, Control plus C. So this is how you write down a signal handler for your shell program. Let me run a process on this shell, sleep 1000, and let me send Control plus C, and you see it terminates. This means that once I write down a handler for the shell, it works for the shell, but it doesn't work for any of the child processes of this shell. On the contrary, I have seen over here, once I ignore a signal on the shell, it is ignored for all the child processes of that shell. Okay, that is really fun. Please practice it. Let us fall back to the slides. Okay, so we have seen the signal numbers and the strings. You see the man page of signal, and now we know what all signals can be sent using the keyboard, and we know we can send signals using the kill command, and we can send signals using the commands like PS, BG and FG. And in a future session we will see how we can send signals using the system calls and the library calls. Fine. And we have seen the signal disposition, and they can be ignored, terminate, code dump, and stopped and resumed. Fine. These are the signal dispositions. Some of the important signals whose default behavior is term are mentioned on this slide. Sig hub, sig int, sig kill, sig pipe, sig lam, and sig term. Their default behavior is terminate the process without generating the code dump file. And these signals will terminate the process as well as will generate the code dump file. Sig quit, sig ill, sig fp, and sig v. And these two signals, the default behavior of these two signals are stop the execution of the process, that is SIG stop and SIG TSTP, and these two signals will actually continue the execution of the stop processes, SIG child and SIG continue. Okay, one more thing, that is masking of the signals. Dear students, you know a signal is generated by some event. Once generated, a signal is later delivered to a process which then takes some action in response to that signal. Between the time a signal is generated and the time it is delivered to the process, that signal is said to be pending. Normally, a pending signal is delivered to a process as soon as it is next scheduled to run, or immediately maybe if the process is already running. Remember, there can be at most one pending signal of any particular type. That is, these standard signals, they are not queued. Sometimes, dear students, we may need to ensure that a segment of code is not interrupted by the delivery of a signal. To do this, we can add a signal to the process signal mask. And a process signal mask is actually a set of signals whose delivery is currently blocked. And if a signal is generated while it is masked or blocked, it remains pending until it is later unmasked or blocked. Unmasked or unblocked, that is removed from the signal mask. Well, this masking of signals, writing our own signal handlers, we will see these concepts, how we can do this within a C program in our next session. So that is all for today's session. And I hope today's session was informative for you all. In the next session, inshallah, we will continue discussing this part, and we'll see how we can send the signals, ignore the signals, write our own signal handlers, create signal masks from within the C programs. Dear students, if you have liked today's session, please subscribe the YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning, and Allah Hafiz.